Welcome everyone. Welcome to this UNSW Stats seminar series. So today we're very, very lucky to have Catherine Calder, or you can call her Kate. So Kate is professor in the Department of Statistics and Data Sciences at the University of Texas at Austin. Prior to that, Catherine was based at Ohio State, if I'm correct, for quite a few years. And Catherine is also associate editor in some of the well-known journals such as Annals of Applied Stats, Bayesian Analysis, and etc. Her research interests lie in spatial stats, Bayesian modeling and computation, and statistical network analysis, to name a few. And so today, Catherine is going to talk about spatial confounding and restricted spatial regression methods. So Catherine, thanks for accepting to give this talk, and the virtual floor is yours.
Great. Thank you so much for the invitation. It's wonderful to be visiting you virtually. I, of course, would have loved to have come in person too, but this is a great opportunity for me, my first talk in Australia. So I'm going to be talking today about spatial confounding and restricted spatial regression methods. This work was done jointly with Corey Kahn, who was a PhD student of mine at Ohio State, and she is now on the faculty at Iowa State University in their Department of Statistics. So this work is more theoretical than kind of what I typically do. But there's actually a kind of a long story leading up to it, where Corey and I, through a particular collaborative project, had started using some of the restricted spatial regression methods that were in the literature and started kind of noticing some bizarre behaviors in some of the simulation studies that Corey was running, and decided that we would kind of look into these issues a little further. And this talk is kind of a result of what kind of came out of that particular process. So if you don't work in spatial statistics or Bayesian methodology, you might not be aware, but this issue of spatial confounding has kind of become very popular in the literature over the past couple of years. And I want to start with kind of giving you an introduction to what is meant by spatial confounding. So to introduce the idea, I'll present a very kind of generic model for spatial statistics. So we'll assume that Y is some observable outcome associated with points in space, and that we can decompose its variation into components mu, eta, and epsilon. Mu is going to be the component of the model that captures large-scale spatial structure. And typically, we're going to specify a model for mu that's going to be of a regression form. So we'll assume that we can write mu as x beta. Epsilon is the non-spatial error that usually we think of as capturing measurement error. So we'll typically assume that it's independent and identically distributed. And what makes this model spatial is the specification of eta, which is a random effect that captures spatial structure, typically small spatial structure that cannot be explained by observable covariates x. So this general framework kind of permeates the literature. It's where I start when I'm teaching a course on spatial statistics. And what Corey and I realized when we embarked on this research is that kind of throughout the literature on spatial confounding, there seem to be certain expectations about beta x, so this regression coefficient in the large-scale spatial structure of the model. And these expectations are that the inclusion of eta should not impact the point estimate of beta x. So the idea is that this, in most situations, we're either interested in predicting unobserved y's, or we're interested in inference on beta x. Very rarely are we actually interested in inference on some component of eta. And so in particular, eta is included in the model really just to get the error specification correct, or the kind of stochastic specification of the model correct. Another kind of common expectation is that eta controls for unobserved covariates. So oftentimes in spatial problems, the missing small-scale spatial structure is precisely what's not observed, and that's why we need kind of a random effect specification for eta. And then finally, because usually we think of spatial dependence as being positive, meaning that things that are closer together are more positively correlated, we think that, or there's an expectation that not including eta in a model, so not accounting for spatial dependence in the model, is going to lead to underestimation of uncertainty in beta x. And there's some reasons to believe number 3 in certain cases. So for instance, if all we were interested in doing is estimating a constant mean, it would be the case that not including eta in the model would lead to underestimation of uncertainty in that unknown mean. But claims about this being the case for a general mean structure are not, in fact, true, despite the expectation in the literature. Okay, so with this background, what is spatial confounding? So there have been several kind of loose definitions that have been put forth in the literature. Clayton et al. In a very famous paper on Bayesian disease mapping suggested that spatial confounding was a way of thinking about the problem of unobserved spatial confounders in disease mapping settings. It's also been used to refer to multicollinearity between the spatially varying covariates, so when X has some spatial structure to it, and a spatial random effect eta. So a problem that has to do with the specification of eta and its relationship to X. And it's also been used informally as an explanation for why these 3 expectations that I had on the previous slide don't hold in practice. Okay, I'll go back one. So over the last, I would say, 15 years or so, there has been a kind of flurry of activity in developing statistical methodology to alleviate spatial confounding. And this is kind of interesting because of the lack of a really formal definition of what spatial confounding actually means. So nevertheless, in this literature, there is, again, an expectation that spatial confounding, whatever it is something that leads to bias in estimates of regression coefficients in spatial models. It leads to overestimation of uncertainty in regression coefficients. And more recently, the issue of dimension reduction, so thinking about computational tools to allow faster model fitting through dimension reduction has kind of gotten mixed up in this literature on spatial confounding, or they've become related for reasons that I will talk about in a second. Okay. So the goal of this talk is to explore the origins of the essential ideas and to revisit some expectations. Okay, so I'll start off with an overview of restricted spatial regression methods in the literature. So to introduce restricted spatial regression methods, I will focus on the spatial linear mixed model. The linear mixed model is not what's typically used. Typically in applications, we're in a generalized linear model setting, but for illustrative purposes, I'll focus on the linear model setting for now. So let's define Y to be a random vector, n-dimensional random vector of observable quantities associated with n non-overlapping regions associated with a partition of space. You can think geographic space and a partition that might correspond to, in the US at least, states, or within states, say counties within states. And this partition is equipped with a graph that I'll denote G, describing a spatial neighborhood structure. So the idea is this graph says which components of the partition are neighbors of other components of the partition. We can use different specifications of a neighborhood structure, but what's commonly used is components of the partition that share an edge or are touching each other are considered neighbors. If they don't, they are not neighbors. And then we encode this neighborhood structure in a binary matrix A. So it has ones and zeros, where the ijth element of A is a 1 if region I is connected to region J or is a neighbor of region J, and 0 otherwise. Okay, so the way this model is specified is using the same decomposition that I'd shown previously. We'll have a regression term, a spatial random effect eta, and an independent error structure epsilon. And this ICAR prior is a prior specification for the spatial random effect eta. It has this particular form here, which looks a lot like the kernel of a multivariate normal distribution. And it is functionally similar to that. The reason why it's not a normal distribution is this matrix Q, which is the Laplacian of the matrix A, is not actually invertible. So it's kind of like an improper normal distribution. And this is a widely used prior this ICAR prior is widely used in spatial modeling. And I am going to parameterize it in terms of precision parameters. So tau squared S is going to be the spatial precision, so 1 over the variance, and then this tau squared epsilon is the precision of the error process epsilon. So this is the general framework. In one of the first paper introducing the idea of restricted spatial regression was to Rich, Hodges, and Zadnik. And they noticed that this spatial linear mixed model with an ICAR prior could be written in the following form. So in particular, replacing the eta that was here previously with a matrix W times a vector delta, where W is fixed and corresponds to the eigenvectors of Q, which is, again, the graph Laplacian of the simple graph A that embeds this neighborhood structure on the partition of space. And delta is now the random component of the model, and the prior distribution, again, this should be proportional, sorry for the typo, is proportional to this form here. So this is just kind of a reparameterization from eta to delta in this particular model. So why is this helpful? Well, we can view this model specified in this way as a more general spatial random effects model, where W here can be any n by q matrix of basis vectors, and F is a symmetric, non-negative, definite matrix. So it uses, the idea is that they use the ICAR specification of the prior distribution on eta to suggest a more general modeling framework where there is a general set of basis functions and a random coefficient on them. And so we're going to remain in this framework and focus on a Bayesian analysis of this model. We'll specify flat priors on the components of beta x and independent gamma priors on the two precision parameters. And in particular, we're going to be focusing on a comparison between models of this form and the corresponding non-spatial model, which just has this spatial random effect term omitted. In particular, we're focusing on comparisons between inference on beta x under this spatial random effects model and this beta x, the coefficient in the corresponding non-spatial model. Okay, so just to further set up this problem, borrowing the motivating example from the Rich et al. Paper, they looked at incidence of, or a data set from Slovenia. In particular, they have districts that partition the country of Slovenia, and they were looking at the association between stomach cancer, so this is the standardized incidence ratio of stomach cancer, and socioeconomic status in each of these regions. So if you look at these maps, it's fairly apparent that there seems to be a negative association between socioeconomic status and the standardized incidence ratio for stomach cancer. It's also apparent from looking at both of these pictures that both the SIR and the socioeconomic status exhibit some spatial tendencies, so positive spatial dependence. Okay, so we focus on the spatial ICAR model and the corresponding non-spatial model, and focus on the inference on the beta corresponding to the coefficient on the effect, representing the effect of socioeconomic status. If we look at the non-spatial model, we get a posterior mean of negative 0.137 with this credible interval. For the spatial model, the coefficient on the socioeconomic status covariate is closer to 0. You'll notice that the credible interval is wider than it is in the non-spatial model. In particular, this credible interval here includes 0, and therefore might be deemed kind of informally as not being statistically significant. So these results were viewed by the authors of this paper as problematic. In particular, the idea being that they fit a regular or a non-spatial regression model. They observed a significant, in quotes, effect of socioeconomic status on SIR. They expected that if they were to fit a spatial version of the model, that the coefficient would be unaffected and the credible interval would get larger, but they didn't expect that it was going to get this large. So they viewed this as overinflation of the variability in the posterior distribution. And so what they did, which is what we call kind of the first restricted spatial regression method, is proposed that instead of using the estimate from the ICAR model, that they actually tweak this model a little bit. And in particular, they noticed that under the ICAR model, the posterior distribution of beta x, conditional on the two precision parameters, has this form here. And what they wanted was for these two posterior means to be the same. And so they suggested selecting W, which is the spatial basis, so that it is orthogonal to the column space of the design matrix X. Okay, so writing this in terms of the spatial linear mixed model that I was showing you before, what they do is they take that W delta that we had before and instead replace it, replace both W and delta with L delta 1, where L is the matrix composed of the eigenvectors of the projection matrix onto the complement of the column space of X. So the idea is they, instead of using the full ICAR basis, which is W, they take only the components of that basis that are orthogonal to the column space of X. And by doing this, they are kind of pushing the posterior distribution of beta X to align with the posterior mean in the non-spatial model.
I didn't get that. Could you try again?
I'm sorry. Turn this off. All right, apologies for that. Okay. Several years later, a paper was published by Hughes and Horan, which embraced this general idea of restricted spatial regression, but made the following two criticisms of the approach. And the first criticism is that they suggested that the RHZ model, so the Rich, Hodges, and Zadnik model here, failed to account for the underlying graph in the construction of L. So this basis L really only depends on X. There's nothing kind of about the kind of spatial basis that is in this component L. They also criticized this is that in some sense L was bigger than it needed to be because it includes negative or repulsive spatial patterns, which are not expected. So what they propose is instead of L, to use instead what they call MQ. And MQ is a n by q matrix of the attractive eigenvectors, so the eigenvectors associated with non-zero eigenvalues of the Moran's operator, which is defined as this. The Moran's operator is the numerator of the well-known Moran's I statistic, which is often used as a measure of spatial dependence. So because this basis, MQ, actually depends on both X and the graph Laplacian, they argued that this was more spatial and therefore a better basis to be using. So again, this model fits into this general framework of a spatial random effects model. We have a basis and coefficients with a prior distribution on delta 1. That should be a delta 1. Apologies for the typo, of this particular form. And then they went on to suggest that maybe you don't actually need all of MQ, that for that perhaps dimension reduction, so instead of using all n by q columns of this matrix MQ, maybe you only needed to use the ones that kind of embed important spatial structure. And to motivate this idea, they also used the Slovenia data set, and they compared L1, L10, and L26 to the counterparts from the Moran operator basis. And you can see here L, these bases don't really look particularly spatial. They look essentially smooth and then like particular kind of hot spots. On the other hand, these bases look much more like patterns of spatial dependence. So they argued that this model was superior to the original proposal. Nevertheless, including or thinking about both of these restricted spatial regression models, remain some concerns in the literature. In particular, one of the concerns was, is this assumption that the columns of X are orthogonal to the columns of the spatial basis, is that too strong? Is that an assumption that we really want to make? Other criticisms come from the Hanks et al. 2015 paper that noted that instances of elevated type S error, which is the Bayesian analog of type 1 error, under model misspecification. Another concern was kind of lack of theoretical exploration. So a lot of this was kind of just more intuitive adjustments to models without actually kind of showing what they formally imply about the actual inferences. And then lastly, all of this was kind of proposed in the non-Gaussian setting, but at least in the disease mapping literature, the kind of non-Gaussian setting with count outcomes is certainly more prevalent. Okay, so moving on to show a little bit about some of the things that we found. Corey decided that she wanted to actually do some theoretical work and actually fully describe the posterior distributions for these classes of models. In order to do that, we had to kind of come up with a formal definition of what spatial confounding means. And we, despite the fact that a lot of people have talked about this issue, there really wasn't a formal definition in the literature. So we say that a method that results in a posterior mean for the coefficient in a spatial regression model, so the marginal posterior of mean of beta x, and marginal posterior variances of the components of beta x, alleviate spatial confounding if the following conditions are met. So the first condition is that the expected value or the posterior expectation of beta x in the spatial model coincides with the marginal posterior mean in the non-spatial model. And then for the components of beta x, we have this ordering of variances. So the restricted spatial regression method, marginal posterior variance, we're saying has to be less than, or sorry, greater than the variance, corresponding variance in the non-spatial model. Again, because we expect that spatial dependence is positive, and therefore there is less information than if we had independent observations. Therefore, we expect inflation of the variance relative to the non-spatial model. And on the other hand, because Rich et al. Had suggested that the ICAR model was overinflating variances, that we want a restricted spatial regression model, the variance is less than or equal to the variance in the ICAR model. Okay, so we sort of have this negative definition of spatial confounding, but this is consistent with the literature. Then using this method, we define a restricted spatial regression model to be any model that's of this form that we've used before, where W is chosen so that the column space of W is orthogonal to the column space of X. So with these two definitions in mind, we showed that this RSR model, defined on the previous slide, gives rise to a marginal posterior distribution of beta x such that the marginal posterior mean of beta x is x transpose x inverse x transpose y, so just the standard OLS estimate of beta. And we also showed that the marginal posterior variance of each component of beta I is less than or equal to the corresponding marginal posterior variance under the non-spatial model. And so this actually was quite surprising to us, because if you remember, we define spatial confounding to have this particular ordering of the variances of the marginal posterior distributions of the beta x's. So we expected the non-spatial model to have the smallest variance. But what we showed, in fact, is that the opposite is true for restricted spatial regression models defined previously. So what this implies is that RSR models that are in the literature doing the exact opposite of what they were supposed to be doing. So in particular, as I've said, they were designed to accomplish this particular inequality, but instead they, in fact, ensure this is going on, which again explains why simulation studies using these methods are not giving the results that people expected. And it turns out that you can trace the origins of this problem to error made in one of the derivations in the original paper. But we kind of took this idea of comparing these marginal posterior distributions a little bit further in our work. And in particular, what we showed is that, again, comparing the marginal posterior distribution of the regression coefficients from an RSR model to the marginal posterior under non-spatial model, that essentially for very large and very small values of beta x, the marginal posterior distributions in an RSR model are essentially the same as they are in a non-spatial model. So we know for sure that the means are the same, but we're also showing that the tails match as well. So the implication here is that RSR models are giving very similar inferences to non-spatial models. The downside, though, is that RSR models are computationally intensive. So if we compare the time it takes to fit these two versions of restricted spatial regression models, very large amounts of time, fitting an ICAR model is not very computationally intensive at all, and can be done very quickly. So RSR models aren't really giving you anything different in terms of inferences compared to non-spatial models, but fitting them is a lot of work. So one implication of our results is that we have this nesting of credible intervals. So oftentimes these models are used, even though they're Bayesian models, we look at credible intervals, whether they cover 0, and that is used as an indication of the importance of particular covariates. And what we show is that the implication of this theorem is that credible intervals for RSR models typically will be nested inside credible intervals for non-spatial models. So RSR models are more likely to find significant, in quotes, effects than their non-spatial counterparts, which again is not kind of what we would expect. So summary, RSR models do not behave as expected, and in addition, I want to point out that these results do not depend on how the data were generated. They're true in general, and these artifacts are not a result of model misspecification. So what about this issue of attractive spatial patterns and dimension reduction? So again, we have a result that essentially says that it doesn't really matter which basis you use. Our results hold under any basis. So restriction to attractive patterns are not going to alleviate any of the problems with RSR models. So what actually are RSR models doing? The way we kind of settled on thinking about it is that they are essentially behaving like an overspecified linear model. So let's imagine, again, not in the spatial setting, we have a standard linear regression model, and we decide to replace the covariate or add covariates to the model so that we replace X, we add covariates to the model that are X and W, where W is chosen so that it's orthogonal to X. So if we do this, the coefficients on x would remain the same, of course, but the posterior variance of the coefficients on x are going to shrink, and they're going to shrink because we've added these kind of synthetic predictors to the model. In particular, we can show that the posterior variance is going to be scaled as follows. If we look at this graphically, actually so this both the residual sum of squares, the RSS, the numerator of the posterior variance, and the denominator are both decreasing functions of Q. So if we just plot this for a particular example, we can see that adding additional covariates, so adding columns of W to the model, essentially are just, again, we're not including the Q here, but we're essentially decreasing the posterior variance. Again, not surprising at all if we think about why we don't add synthetic predictors to standard regression models. Implications of this for inference on beta x. So if W is not useful, meaning that the ratio of the spatial standard deviation, or the signal to noise ratio, is small, inference on beta x is going to be essentially the same as what we would have gotten if we had fit a non-spatial model. The worse x is at explaining the variability in y, the more likely x is deemed to be significant, which is a really horrible property for a model. And then lastly, the more spatial basis vectors we add to the model, we're more likely to conclude x is significant. So therefore, this kind of selection of basis functions, or dimension reduction, that modeling decision, which is proposed as a computational technique, is sort of driving inference in these models, which I think is not something that we would want to happen. So in particular, RSR models will always have elevated type S error rates, so the Bayesian analog to type 1 error rates, relative to the non-spatial model. Just to look at this a little bit more closely in the context of a particular example, this is another famous spatial data set from Melanie Wall's 2004 paper that looked at comparing the SAR and the CAR models. So here we have the 48 contemporaneous states of the in the US, and we impose a neighborhood structure that says states are neighborhoods of each other if they touch each other. And what we have here on the left is the SAT, the average SAT score in the states. So realizing that I'm speaking to an international audience here, this plot would be a little bit surprising. Typically, we wouldn't expect kind of the central United States to have the highest SAT values in the higher than the entire US. And what's going on here is that looks like I didn't put the plot here. Sorry about that. But the interesting thing about this is we have covariates, which is the number of people who take the test. Fewer people take the test in the central United States. And so we have this inverse relationship between the number of test takers and the score on the SAT test. The plot that's most interesting in the context of what we're trying to show here is we actually fit a restricted spatial regression model with dimension reduction and computed the variance of beta 1, this effect of number of test takers, as a function of the number of spatial basis functions used. And we don't have monotonic decrease because, again, there's this scaling by Q, but we can see this general pattern of this kind of variance bumping around, but generally decreasing as we include more and more spatial basis vectors, which again is not really a desirable property. Like, we don't expect small changes in the number of basis functions to have such an implication for inference on beta. So with our work, there are still some unanswered questions. Do RSR models reduce bias and point estimates? That's a kind of trickier question to answer in general. If they do, when? Are type S error rates always elevated for RSR models? We can't say that for sure. That depends on how the data are generated. They do relative to the non-spatial model. Do results hold for non-Gaussian data? In our paper, we include a bunch of simulations that indicate that they do, but we don't have formal results. And then finally, what is the right model here? So much of this is just kind of model comparison, and we don't have necessarily implications for what actually should be done. In terms of our simulation studies and then examples in the literature, what we have found in practice is that non-spatial versus ICAR models really only differ in terms of inference on beta x only when the estimates of beta x are small. So if you have strong effects of covariates, it probably doesn't matter whether or not you fit a non-spatial or an ICAR model. Lastly, I just wanted to mention that there's some important connections between this work and causal inference. So as I mentioned, one of the first introductions of phrase confounding in the spatial statistics literature is this issue of confounding by location. So again, kind of this idea that in order to be able to pick up kind of true causal effects, we need to control for unobserved confounding. Hodges and Rich argue that fitting a spatial model does not, in fact, correct for unmeasured confounders, and I think that's something that I would agree with as well. However, Chris Pachorik in a statistical science paper actually showed that in some cases it actually can. So under certain types of spatial dependence, it's actually possible that a spatial model can formally correct for unmeasured spatial confounders. There's a lot of work in these areas, in particular kind of moving away from regression adjustment approaches to using other tools that are available in the causal inference literature, like propensity score matching. So I will finish up here. This paper that I presented should be appearing in JASA soon, and it's already available on the website. Thank you very much.
Thanks, Kate. That was a very interesting work that you presented. Is there anyone in the audience that would like to ask a question? Okay. Okay, Kate, maybe I'll start with one.
Okay.
So at some point you were saying that the variance of the beta I in the non-spatial case were expected to be lower than the ones that you get in the spatial with the spatial model. But then you proved that it was the opposite. Why is that? What, like, is there some, what's the reason?
So, yeah, I'm having trouble. Oh, here I go. Trying to see if I can go back to this. Yeah, so no, that's a great question. So based on kind of the discussion in the literature, this was the expectation for the ordering. So in particular, for a restricted spatial regression model, we expect the variance of the coefficients to be larger than they are in the non-spatial model. And so this isn't something that was true. It was more kind of like, this is a property that you would expect given the way, or this is more consistent with expectations. And it comes from this idea that if you are just trying to estimate, say, a mean, and you have positive dependence between your observations, if you ignore that positive dependence and assume you have independent measurements, your confidence interval for your mean is going to be smaller than it actually should be. So this is kind of what people were expecting, and then what we showed was in fact this solution, which is kind of requiring that the spatial basis is orthogonal to the column space of X, actually does the opposite. And in fact, you don't get this anymore. Does that help at all?
Yeah, okay. I thought that, there was maybe some result in the first place, but no, it was kind of expected, but not proven.
It was an expected, yes.
There are two comments in the chat. One is from Scott, and now David is writing one as well. I don't know if you can see them. Scott says, just wanted to say that I didn't have much knowledge of spatial confounding issue before this talk, so consider me educated. But I really enjoyed the talk and think this is very nice work. Well done. And then there's a question by Malcolm. Sorry if this is overly naive, but do these results imply that unrestricted spatial models, like ICAR, are more generally useful than RSR models? So maybe you can take this one and then we'll look at David's question.
Sure. So no, that's not a naive question at all. And I have to think about it a little bit in terms of how I would answer it. So first, I would agree that it definitely depends on the situation, whether or not, so it is hard for me to imagine a situation where you would want to fit a restricted spatial regression model. But in terms of whether you want a non-spatial model or an ICAR model, that is very context specific, and I don't have a good answer for that. The only thing that I will say is based on our simulations and then examples from the literature of when people compared fitting an ICAR and versus a non-spatial model, it seemed like the only time it really made a difference was when the coefficients are very small. So in that case, you might actually get something different. If you have strong effects, then then your conclusion is likely not going to depend on whether you use a non-spatial or an ICAR model. And I will say, though, that I found this answer to be somewhat unsettling in work with collaborators who were actually the project kind of motivated some of this work, because again, you know, in theory, you don't know what the effect actually is. And we spent all this time working on restricted spatial regression methods, thinking that was the answer. And we said, no, it's not. We have to pick either a non-spatial or an ICAR model. And that's not a very kind of, again, satisfying example. What I tend to do in practice is recommend fit multiple models and make sure your conclusions are robust to the assumptions you make. But I can imagine situations where that's not a very satisfying example.
Thanks, Kate. I'll read David's comment/question. Nice talk. Hodges and Reich argue that which method you would use depends on your research question. So, for example, the suggested RSR for situations where you want to correct for effects or violations of independence on SEs, but did not want to partial out spatial trends present in fixed effects. Just wondering what your thoughts are on how the method you would use to incorporate spatial effects depends on what the model objective is.
Yeah, so I think my answer to this question is kind of the same as the one I gave to the previous questions. I don't actually know what Hodges and Rich would argue for. I have heard some of Jim Hodges' reactions to our work, and he is more thinking now about that we should use completely different approaches to thinking about spatial confounding and excessive. If we're really interested in estimating effects, we shouldn't be using regression methods. So he's kind of gone in that direction. And I'm not sure what Brian Rich would say. My thoughts again are, I can't imagine a situation where I'd use RSR models, but whether or not I'd use an ICAR, non-spatial, or some other model, that probably is application specific.
Thanks, Kate. I think David is happy with your answer. I think we just went a little bit over time, so well, thank you again for giving this great talk and taking the time to speak to us. That was very nice.
Yeah, thank you so much for the opportunity.
And yes, there's a recording, so Kate, if you want the recording, I can send it to you if you want to use it. I can send you the video.
Okay, great. Thank you.
And thanks everyone for attending as well.
Bye.
See you, Kate. Have a good evening.
You too.